There is a paradox in the cosmos that has haunted astronomers since the moment we first turned our glass eyes toward the heavens. The paradox is this: the brighter the light, the deeper the shadow it casts. We tend to think of darkness as the enemy of discovery. We build massive observatories in the most desolate, pitch-black corners of the planet to escape the glow of our cities. We launch billions of dollars of gold-plated mirrors into the void of space to escape the faint luminescence of the atmosphere itself. We are obsessed with gathering light. But there is a cruel irony waiting for us when we finally focus on the most important targets in our galaxy. When we look at a star, we are not seeing the star. We are seeing the glare. Imagine trying to spot a firefly hovering next to a searchlight that is pointing directly into your face. The firefly is there. Its light is traveling toward you. But it is utterly annihilated by the overwhelming power of the main beam. This is the reality of hunting for exoplanets, hidden companion stars, and the subtle structures that dictate the evolution of solar systems. We know they are there. The mathematics tells us they must exist. The gravitational wobbles suggest their presence. But we remain blind to them, dazzled by the very stars we are studying. For decades, the scientific community believed that the only way to solve this problem was brute force. We thought we needed bigger mirrors, larger shields, and telescopes floating millions of miles away from Earth. We accepted that from the ground, looking through the thick, turbulent soup of our atmosphere, we had reached a hard limit. But we were wrong. While the world was looking at giant engineering marvels, a team at the University of California, Los Angeles was looking at something much smaller. They were experimenting with a technology that does not require a rocket to launch or a mountain to hold it. They were working on a device that fits in the palm of a human hand, yet possesses the power to strip away the blinding veil of a star and reveal the ghosts hiding in the glare. They realized that the problem was not the telescope. The problem was the light itself, and how it behaves when it crashes through the air we breathe. To understand why this breakthrough is shattering our understanding of what is possible, you have to understand the enemy. The enemy is the Earth's atmosphere. To a telescope, the air above us is not clear. It is a chaotic, churning river of gas currents, temperature shifts, and density pockets. When starlight hits the upper atmosphere, it is a perfect, flat wave. It is pristine information from across the galaxy. But as it travels down through the layers of air, that wave gets broken. It gets twisted, shoved, and refracted. By the time it hits the mirror of a telescope on the ground, that perfect image has been shattered into 1,000 dancing fragments. Astronomers call this speckle noise. If you look at a star through a high-powered ground telescope, it doesn't look like a steady point of light. It looks like a boiling pot of white lava. It dances and jumps around the frame. This dancing is the atmosphere scrambling the data. It is the reason why stars twinkle when you look up at night. That romantic twinkling is actually the destruction of information. For a century, this turbulence has set a hard ceiling on what we can resolve. We could see the star, yes, but we could not see the faint, delicate structures orbiting it. They were washed out by the boiling light. Engineers tried to fix this with adaptive optics. They built mirrors that can bend and flex thousands of times a second to counteract the movement of the air. It was a brilliant solution, and it allowed us to see things we never dreamed of. But even adaptive optics has a limit. It can correct the image, but it cannot fully separate the blinding light of the star from the faint whisper of a planet or a disk right next to it. The glare remains. The firefly is still lost in the searchlight. The data is still contaminated. But the radiation readings and the spectral analysis were just the beginning. What the team at the University of California found inside the mechanics of fiber optics would defy the conventional physics of observation entirely. They realized that if you cannot stop the atmosphere from scrambling the light, perhaps you can catch the light and unscramble it after it arrives. This is where the concept of the Photonic Lantern enters the narrative. It sounds like something out of a fantasy novel, but it is a piece of hard engineering that is redefining precision. The device is essentially a specialized glass thread. But unlike a normal fiber-optic cable that just carries light from point A to point B, the Photonic Lantern is designed to change the shape of the light as it passes through. It acts as a mode converter. Think of the chaotic, scrambled light coming from the telescope as a noisy room where everyone is shouting at once. The atmosphere has mixed all the voices together. The star is screaming, the turbulence is yelling, and the hidden structures are whispering. A normal telescope just records the noise. The photonic lantern takes that chaotic noise and forces it through a channel that separates the voices. It takes the scrambled starlight and organizes it into distinct patterns. It physically separates the light that is the star from the light that is the noise. It turns the telescope into a noise-canceling headphone for the cosmos. By analyzing how the light moves through this microscopic tunnel of glass, the system can mathematically subtract the turbulence. It can look at that boiling pot of speckle noise and reconstruct the still, silent image that lies beneath it. It gives a telescope on the ground, sitting under miles of heavy air, the clarity of a telescope floating in the vacuum of space. The theory was sound. The mathematics worked on paper. But theory is not discovery. To prove that this tiny strand of glass could humiliate billion-dollar observatories, they had to take it to a legend. They took the device to the Palomar Observatory in San Diego. They hooked it up to the Hale Telescope. This machine is a titan of astronomy. For decades, it was the largest telescope on Earth. It has discovered quasars and mapped the expansion of the universe. But even the Hale Telescope had never seen what it was about to see. The target was Beta Canis Minoris. This is not a mysterious, distant quasar. It is a bright star, visible to the naked eye, sitting in the constellation of the Little Dog. It is a star we thought we knew. It has been catalogued, photographed, and studied for generations. But we had only ever seen it through the dirty window of the atmosphere. We had seen the glare, but never the source. The team connected the photonic lantern to the massive 200-inch mirror. The tension in the control room was the quiet kind, the heavy silence of scientists waiting to see if years of work will dissolve into static. They weren't just looking for a clear image. They were looking for a specific signature. They were hunting for a companion. Previous data hinted that Beta Canis Minoris might not be alone, but the glare was always too bright to confirm it. If the lantern worked, it would cancel out the blinding light of the primary star and reveal the darkness next to it. They initiated the capture sequence. The massive telescope tracked the star across the night sky. The light poured down the tube, bounced off the primary mirror, focused into the secondary, and was funneled not into a camera, but into the tip of the photonic lantern. Inside the microscopic glass throat, the light was torn apart and reorganized. The turbulence of the California sky was stripped away layer by layer. On the monitors, the data began to populate. Usually, looking at a star like this involves heavy post-processing. You have to take thousands of images and average them out to guess what the object looks like. But the lantern was doing the work in real time. The signal-to-noise ratio began to climb. The chaotic dancing of the speckle noise flattened out into a straight, clean line. And then, the image resolved. The blinding wash of white light that usually drowns out the sensors was dampened. The lantern had successfully suppressed the star's glare by a factor that seemed impossible for a ground-based instrument. The center of the frame cleared. And there, emerging from the digital noise like a ship coming out of the fog, was a structure. It wasn't just a point of light. It was a definite, resolved presence orbiting close to the star. The resolution was so sharp, so precise, that it rivaled the capabilities of an interferometer, an array of telescopes that spans hundreds of meters. But this was done with a single mirror and a piece of glass you could hold between your fingers. They weren't just seeing a star, they were seeing the invisible architecture of a solar system that had been hiding in plain sight for all of human history. But the clarity of the image revealed something else. As they analyzed the light coming from the newly revealed companion, the data didn't match the standard models for a simple binary system. The light signature suggested an interaction, a proximity that shouldn't be stable. The lantern hadn't just cleaned up the picture, it had exposed a gravitational anomaly that we had been blind to for centuries. And as the team looked at the readings, they realized this was just the first target. If Beta Canis Minoris was hiding this, then the sky was full of ghosts waiting to be found. And these ghosts are not rare. They are everywhere, orbiting nearly every star we have ever named, hidden only by the limitations of our own vision. The discovery at Beta Canis Minoris was not an accident, it was a proof of concept that threatens to dismantle the hierarchy of modern astronomy. Until this moment, if you wanted to see the faint detail of a star system, you had two choices. You could wait for a space telescope like Hubble or James Webb to free up time in its schedule, which could take years. Or you could build an interferometer. An interferometer is a beast of engineering. It involves taking multiple telescopes, spacing them hundreds of meters apart, and combining their light signals with a precision measured in nanometers. It is expensive, it is complex, and it is rare. There are only a handful of facilities on Earth capable of doing it effectively. It was the exclusive province of the scientific elite. But the photonic lantern changes the geometry of power. It takes the resolving power of a giant array and collapses it down into a single optical fiber. It democratizes the deep view. It means that the telescope in your university backyard could suddenly possess the vision of a machine worth billions. To understand how it achieves this impossible clarity, we have to look deeper into the throat of the device itself. When the team at the University of California designed the lantern, they were not thinking about lenses. They were thinking about modes. In physics, light does not just travel as a straight line. It travels as a wave, and that wave can vibrate in different shapes. These shapes are called modes. Think of a guitar string. When you pluck it, it doesn't just vibrate back and forth. It vibrates in a complex pattern of standing waves. Light does the same thing. When starlight hits the atmosphere, the clean, single mode of the wave is shattered. It gets excited into hundreds of chaotic, high-order modes. This is the noise. This is the blur. A normal camera sensor cannot tell the difference between the clean mode of the star and the chaotic modes of the atmosphere. It just collects all the photons and gives you a blurry blob. But the photonic lantern is a discriminator. It is a filter for reality. The device begins as a bundle of multiple fibers, fused together into a single, tapered tip. As the scrambled light from the telescope enters this tip, the lantern forces the light to separate. It guides the chaotic, atmospheric light into one set of channels, and the stable, pristine light from the star into another. It physically disentangles the knot. By measuring the intensity of light in each of these separate channels, a computer can reverse engineer the image. It can mathematically delete the atmosphere. The result at Beta Canis Minoris was a reconstruction of light that should have been impossible to see. The data revealed that the companion star was not just a theoretical mass affecting gravity. It was a tangible object with a specific luminosity. The separation between the main star and its hidden partner is incredibly small, roughly the distance between our Sun and Saturn. At a distance of 170 light-years, distinguishing that gap is like trying to see a dime next to a lighthouse beam from 500 miles away. The glare of the primary star is usually 1,000,000 times brighter than the companion. In any other telescope, the companion would be swallowed whole. But the lantern saw it. But the radiation readings were just the beginning. What they found inside the data stream would defy physics entirely. As the team processed the signals, they realized the lantern was doing more than just imaging. It was performing spectroscopy on the companion itself. Spectroscopy is the holy grail of astronomy. It is how we know what things are made of. By analyzing the spectrum of light, we can tell if an atmosphere has oxygen, methane, or carbon dioxide. Usually, this is impossible for close-orbit companions because the spectrum of the main star contaminates everything. The photonic lantern solved this. Because it physically separated the light before it hit the detector, it allowed the astronomers to isolate the spectrum of the faint companion from the overwhelming fire of the parent star. They could analyze the chemistry of a hidden world while it was sitting right next to a nuclear furnace. This is the key that unlocks the door to the next great discovery. If we can read the chemistry of a star's companion, we can read the chemistry of its planets. We are no longer just looking for dots moving across a screen. We are looking for textures. We are looking for weather. The implications for exoplanet hunting are staggering. Currently, to find a planet, we usually wait for it to pass in front of its star, blocking a tiny fraction of light. This is called the transit method. It is effective, but it is limited. It only works if the planet's orbit is perfectly aligned with Earth. It means we miss the vast majority of worlds out there. With the Photonic Lantern, we don't need the planet to cross the star. We can suppress the star's light and see the planet directly. We can see the light reflecting off its oceans or its clouds. We can hunt for worlds that do not want to be found. The team at the University of California estimates that this technology could allow existing ground-based telescopes to detect planets that are currently invisible to even our most advanced space observatories. We could revisit systems we thought were empty and find them teeming with worlds. But as the excitement of the Beta Canis Minoris discovery settled, a darker realization began to take hold. If the atmosphere has been blinding us this effectively for this long, what else have we missed? The universe we think we know is a map drawn by blind cartographers. We have charted the bright, loud objects, the massive stars, the screaming quasars, the exploding supernovas. But the quiet things, the faint things, the things that lurk in the shadows of the giants, they have remained invisible. There is a concept in astronomy called the confusion limit. It is the point where individual objects are so crowded together that a telescope cannot tell them apart. It creates a floor of noise that hides everything beneath it. The Photonic Lantern pushes that floor down into the basement. It opens up a new volume of space to exploration. It allows us to peer into the dense cores of star clusters, where stars are packed like sardines, and pick out individual solar systems. It allows us to look at the center of our galaxy, where the supermassive black hole resides, and see the stars dancing on the edge of the event horizon with a clarity we never thought possible from the ground. The test at Palomar was just the first shot in a revolution. The technology is scalable. The device itself is small, robust, and relatively cheap to manufacture. It does not require a billion-dollar budget or a congressional hearing to approve. It can be retrofitted onto telescopes in Chile, in Hawaii, in the Canary Islands. Within a few years, we could have a global network of lantern-equipped observatories, all staring up at the night sky, stripping away the glare, and revealing the hidden architecture of the cosmos. However, the universe has a way of punishing clarity. When you remove the veil, you do not always like what you see. As we refine this technology, we are approaching a threshold. We are getting closer to the point where we will not just see stars and gas giants. We will see rocky worlds in the habitable zone. We will see the glint of atmospheres that look suspiciously like our own. And that is where the danger lies. Because finding a world is one thing. Understanding what is happening on its surface is another. The Photonic Lantern acts as a probe into the private lives of stars. At Beta Canis Minoris, it revealed a binary dance that had been obscured for eons. But as we turn this eye toward other targets, red dwarfs, unstable variables, and systems with chaotic debris disks, we are going to find anomalies that defy our models. We are going to find systems that look artificial. We are going to find chemical signatures that should not exist in nature. The silence of the universe might not be empty. It might just be hidden behind the glare. And now, for the first time in human history, we have a pair of sunglasses that can look directly into the sun and see what is standing in front of it. The question is no longer, can we see them? The question is, are they watching us back? And that possibility changes the calculus of our existence. If we assume that the universe is teeming with life, we must also ask why it is so quiet. This is the Fermi paradox. But the Photonic Lantern suggests that perhaps the silence is an illusion created by our own blindness. We have been like a person standing in a crowded stadium, wearing a blindfold and earmuffs, wondering why we are the only ones there. We have been unable to separate the signal from the noise. But as we begin to deploy these devices on telescopes across the planet, we are effectively taking the blindfold off. The implications extend far beyond just finding binary stars or gas giants. The real prize, the one that every astronomer dreams of but speaks of only in hushed tones, is the detection of a technosignature. A biosignature is the footprint of life: oxygen, methane, chlorophyll. But a technosignature is the footprint of civilization. It is the spectral evidence of industrial pollution, of artificial lighting, of massive energy harvesting structures. For decades, the search for technosignatures was hampered by the glare. If a civilization was advanced enough to build a Dyson swarm, a massive array of solar collectors around their star, the light from that star would be altered. It would dim in specific patterns. It would radiate excess infrared heat. But without the ability to resolve the star from the noise of our atmosphere, those subtle shifts were lost. The photonic lantern changes this. It gives us the precision to distinguish between natural starlight and the waste heat of an alien industry. We are entering an era where ground-based astronomy is about to overtake our capabilities in space. The sheer size of mirrors we can build on Earth dwarfs anything we can launch on a rocket. The extremely large telescope, currently under construction in the Atacama Desert, will have a mirror 39 meters across. When you combine a light bucket that size with a photonic lantern that can cancel out the atmosphere, you create a machine that is capable of imaging the surfaces of exoplanets directly. We will not just see a dot. We will see continents. We will see weather systems. We will see the seasonal shift of vegetation moving across the face of a world 50 light-years away. But the radiation readings were just the beginning. What they found inside the crater would defy physics entirely. This recurring thought keeps astronomers awake at night, the idea that we are about to find something that contradicts our definition of natural. The photonic lantern is the tool that will force us to confront these anomalies. It allows us to look at the habitable zones of red dwarf stars, the most common stars in the galaxy, and filter out their violent flares to see the planets huddled close for warmth. These are the worlds where the stakes are highest. Red dwarfs are volatile. They blast their planets with X-rays and ultraviolet radiation. For a planet to survive there, it needs a shield. It needs a thick atmosphere or a powerful magnetic field. Until now, we could only guess if those planets were barren rocks or protected havens. With the spectral analysis capabilities of the lantern, we can now sniff their air. We can look for the heavy ozone layer that suggests a planetary shield. We can look for the water vapor that suggests an ocean surviving against the odds. This brings us to the edge of a terrifying realization. We tend to project our own fragility onto the cosmos. We assume that life requires a blue sky, a yellow sun, and a gentle breeze. We assume that water boils away in the heat and freezes in the cold. But the universe is a place of extremes, and chemistry is stubborn. The more we look with these new eyes, the more we find that the rules we learned in school are merely local suggestions, not universal laws. We are finding structures that shouldn't exist. We are finding planets that are too big for their stars, stars that are too old for their galaxies, and signals that persist in environments that should be sterilized. The photonic lantern at Beta Canis Minoris peeled back one layer of the onion, revealing a companion star. But the next layer might reveal a planet that is burning, yet wet. A world that is being roasted by its sun, yet holds onto its oceans with a grip that defies thermodynamics. It forces us to ask, what if life doesn't hide in the quiet, safe corners of space? What if it thrives in the fire? What if the glare we have been trying to filter out is actually the energy source for a type of biology we haven't even imagined? We are refining our vision to find Earth 2.0, but we might be stumbling upon something far more alien. We are looking for a mirror, but we might find a monster. The breakthrough at UCLA is a triumph of human ingenuity. It proves that we do not need to leave the planet to explore the galaxy. We just needed to learn how to see through the air. But it also serves as a warning. The clearer our vision becomes, the less room there is for comfort. The shadows are shrinking. And when you shine a light into the dark, you have to be prepared for what looks back. We are now finding things in the glare of stars that shouldn't be there. We are finding steam worlds and lava oceans that maintain atmospheres despite being bombarded by radiation. The photonic lantern allows us to see the structure, but the spectral data from our space telescopes is already painting a picture of these hellscapes. One such anomaly has just been confirmed, and it challenges every model of planetary survival we possess. It is a world that orbits a red dwarf, locked in a gravitational embrace that keeps one side in eternal darkness and the other in eternal fire. By all accounts, it should be a dead, dry skeleton stripped by its violent star. But the data shows a clear signal of water. Is this the first proof of a steam world surviving against the odds? Or have we been tricked by a cosmic illusion hiding in the star itself? The answer changes everything we know about finding life in the universe. If you want to understand how a planet can hold onto its water while burning at 800 degrees, and why James Webb's latest discovery on GJ 486b is causing a crisis in astronomy, you need to listen to this file next. Until next time, keep looking up.